So the first case we want to look at in motion in 2 and 3 dimensions is the case of projectile motion. What we mean when we say projectile motion is that there is a coordinate direction along which Newton's first law holds. So there is no net force, the velocity is constant. In another perpendicular direction, there is a force causing an acceleration. For a lot of what we're going to deal with, that force is gravity. The acceleration is acceleration due to gravity, 9.8 meters per second squared, directed towards the center of the Earth. Most difficulty that people have with understanding projectile motion comes from wrapping your head around the idea that the motion in those two spatial dimensions is completely independent of one another. When I throw a ball horizontally, it doesn't want to stay in the air longer because I threw it. It would stay in the air just as long as if I dropped a ball from the same height. The free fall motion vertically is completely independent of the uniform translation horizontally. The only thing that couples together those two spatial dimensions of motion is time, because there's only one time coordinate. It's the same time for all. Nice illustration of the independence of the two spatial dimensions in projectile motion is this stop motion photograph, which is one of my favorite physics photographs. So the ball to the left, the red ball, is just dropped. And at the same instant the red ball is dropped, the yellow ball is launched to the right at a uniform constant velocity. I can tell that it is a uniform velocity because every interval of time, that center of the ball is advancing the same amount, right? I always have like the same overlap from one ball to the next. The vertical motion does not show that. Vertically, the balls, the red one and the yellow one, are pretty close to like agreeing at the same height at all the times. But the spacing between balls as the time interval goes on is getting bigger and bigger and bigger. And that's reflecting the fact that as an object is in free fall, its speed keeps increasing, so it keeps covering more and more distance the longer it's in free fall. So in the same interval of time as that the balls move from there to there initially, in the last time interval that hits in this image, they fall a much greater distance. So we have acceleration in one dimension, uniform translation in the perpendicular direction. Those two have nothing to do with one another. The red ball and the yellow ball are both falling the same way. The only thing that is different is that there is a horizontal velocity for the yellow ball. Okay. Some equations for projectile motion in that special case. In the horizontal direction, as I said, we just have uniform translation. So the horizontal displacement is just the initial x component of velocity times time. We can write that out in terms of the initial speed v0, and then that is the adjacent side for the launch angle theta 0. So the x coordinate just gets bigger linearly with time. In the vertical direction, that is not the case. The vertical displacement, we have a part that looks the same. It depends upon the initial vertical velocity times time. We also have a part that grows quadratically with acceleration. And for projectile motion, if we have our convention that up is the positive direction, then the acceleration due to gravity is going to always be minus g, where g is 9.8 meters per second squared, or 9.81 if you want to be careful, or 10 if you want to be less careful. V0y, the initial y component of the velocity, we can split up into the initial speed times sine of the launch angle. And we have an equation for how the vertical velocity changes with time. So the vertical velocity at a later time is the initial vertical velocity, and it is going to become more negative due to the minus gt term. We can play around a little bit with these equations for the horizontal displacement and the vertical displacement and get an equation that is basically the equation of a parabola. So y is a function of x. So y at some time is the initial value of y. We'll have a term that goes as the x displacement times tangent of the launch angle, and then we'll have a quadratic term. So there's our quadratic term in x minus x naught. So plotting this out, giving you your familiar parabola for projectile motion, the motion of a soccer ball, motion of a basketball on a free throw, baseball hit from a bat. And then all of these parabola are in fact a segment of an ellipse, where one focus of the ellipse is the center of the Earth, the gravitating body that is causing the projectile motion. A special case to think about for projectile motion is the case of the range for a projectile that is launched and lands at the same height. Okay. The range R is the horizontal displacement. We have a vertical height or vertical displacement when it begins and ends at the same height. That vertical displacement is 0, giving us another equation that we can use. And we combine those equations together to give an equation for the range. Basically, you are getting the time out of the vertical displacement equation and substituting it into the horizontal displacement equation. The upshot of that is the range is twice the initial speed squared over g, and then times the sine and cosine of the initial launch angle. And there's a nice little trig identity that 2 sine theta cosine theta is the same thing as sine 2 theta. And this gives us one of the immediate results for projectile motion. The optimal range, the maximum range, is going to attain when the launch angle is 45 degrees, because then twice 45 degrees is 90 degrees, and that gives you the maximum value of sine theta being at 1. Another thing to note about the form of this equation for the range is that the range for projectile motion is going to be the same for pairs of angles that are equal amounts above and below 45 degrees. Like, so 50 degrees and 40 degrees have the same range. One is just in the air longer, right? So forth and so on. All right, let's try some questions. So this one working a little bit out. Stuntman for a movie has to jump from one roof onto another roof located 2 meters below. And the buildings are separated by a distance of 2.5 meters. What is the minimum horizontal speed that the stuntman must have when jumping the first roof to have a successful jump? So try to work that out, given what you know about the equations of kinematics, to see what that horizontal speed has to be. Confer with your physics friends about if you agree on what that answer is, and then when you're ready, unpause the video and we'll catch up together. All right, so the answer is 3.9 meters per second is the minimum horizontal speed, which, you know, that double that, and that is the speed in miles per hour. So it's, you know, less than 10 miles per hour. It seems something attainable by a human being. might be a little winded for having done it. And you arrive at that 3.9 meters per second because it takes about 0.64 seconds to fall 2 meters. And so you have 0.64 seconds to go 2.5 meters horizontally. And 2.5 meters divided by 0.64 gets us to just short of 4 meters per second. Okay. Another question for projectile motion. A toy rocket is launched at an angle of 45 degrees with a speed of v naught. There is no air resistance. At what point during the time that is in the air does the speed of the rocket equal a half v naught? So it's launched with a speed v naught at an initial angle of 45 degrees. At what point along its trajectory is it going to have a speed equal to a half v naught? So think about what you think the answer is, and then talk it over with your physics friends, and then we will reconvene. All right. It is, well, you might get mad. There is no time during the flight. Not really a trick question. It's a question about, do you understand projectile motion? The horizontal speed that the toy rocket has is constant because there is no acceleration left, right. That means that the initial horizontal launch speed, which was v0, oops, maybe I should not do it with that pen. That seems bad. Let's try this. V0. Yeah, that looks nice and clunky. Over root 2. That is equal to the x component, comma, x. All right, that never changes. So even at the highest point where the vertical velocity goes through a 0, because if it's at its highest point, it is not going up anymore and it has not yet begun to fall. So its vertical velocity is 0. At that point, it's still moving faster than a half v naught. The slowest it will ever go on that trajectory is v naught over root 2. So there is no time it travels that slow. All right. A few more questions on some ideas in projectile motion. All right. This is sort of an awkwardly worded question, but it does actually get to a point, and the point is worth it. So I still like asking this question despite it being awkward. So in the situation here, we have a gun that is aimed directly at a dangerous criminal hanging from the gutter of a building. The target is well within the gun's range, but the instant the gun is fired and the bullet moves with a speed v0, the criminal lets go and drops to the ground. What happens? Does the bullet hit the criminal regardless of the value of v naught? Hit the criminal only if v naught is large enough, or does it miss? Okay, make sure you go through and understand the wording of the question. Think about which of those 3 cases makes sense and you have an argument for, and then try that argument with your physics friends. All right, that projectile is going to hit regardless of the value of v naught, provided that it was within the range. So that being within range means that the projectile just doesn't go and then land on the ground before it reaches the building. And so here's the key that I want you to understand about this and why this is a worthwhile question. The effect of gravity on the trajectory of the bullet once it's fired is to have it free fall below this straight line. So the bullet is initially going to follow that pretty closely, but then gravity is going to cause it to free fall below the straight line trajectory. And here's the key. However long the person is in free fall, starting from rest vertically, is the same time that the bullet is in free fall below the straight line trajectory. They're both in the same gravitational field. They both have the same gravitational acceleration vertically, and they're in free fall for the same amount of time. So just as far as the person falls, the projectile also falls. So as long as the conditions in the question are true, that the target is well within the gun's range, so it's not doing something like that, right? And the instant the gun is fired, the criminal lets go. They always have to hit. Okay. And then one last one for projectile motion. All right. Battleship simultaneously fires 2 shells at enemy ships. If the shells follow the parabolic trajectory shown, which ship gets hit first? And be careful about what the assumptions in this question are. These 2 shells are fired simultaneously, and you're given the parabolic trajectories. Which ship is going to get hit first? Think about what you think the answer is, and then confer with your physics friends to see if you agree. All right, the answer is B, and I'm going to try to help you see how that can be like an immediate and clear answer. So which of the 2 projectiles, A or B, is actually in the air longest? Well, when the projectile has reached the highest point along its trajectory, that is the point where its vertical velocity is 0. So the time in the air for projectile A is twice the time it takes to fall that vertical distance starting from rest. And for projectile B, the time in the air is twice the time it takes that projectile to fall that distance. Okay. So the distance that projectile A has to fall is clearly greater than B. Therefore, the time in the air is greater for A than for B, right? And therefore, since the time in the air is greater for A than for B, projectile B hits ship B first. Okay. So they're not launched at the same initial speed. Okay. But what is true is that they're launched simultaneously, and you get to see the trajectory that each one follows.